Okay, we're continuing on. We were talking about molarity, I think, last time, which is moles per liter. Remember, that is the most common sort of unit of concentration that we come across. Um, we also will rearrange this. Liters is moles per molarity, or divided by molarity. And if you want moles, which is a very common conversion, liters times molarity. Once again, as we talked about last time, if you do have the big M, you do really want to kind of get rid of it and use really both of those units, the moles and the liters. The number always stays with the moles part, and it's always per 1 liter. And again, that way you won't forget about sort of the liters part of it. We talked about really dilutions as well, I think. And dilutions when we add more solvent. A lot of times that is water, but water doesn't always have to be the solvent. It can be other things. But when we do a dilution, because we're only adding solvent, really the moles of the solute and the moles of the solute before and after the dilution will basically remain the same. And there is a dilution equation, which is M1V1 equals M2V2, or if you want to use a more generic, C1V1 equals C2V2, where C is concentration, V is volume, M is molarity, and V is volume. As I might have mentioned before, again, this is really a dilution equation. That's really where you should use it anytime you do any type of dilution. You shouldn't use it for other type of calculations because you might get it wrong. More specifically, you might get it wrong if you do any type of solution stoichiometry. Now, remember with solution stoichiometry problems, they're basically the same as regular stoichiometry problems. They could be a regular stoichiometry problem. They could be a limiting reagent type problem. But really the main difference is a lot of times we will use molarity and volume to get moles. So a lot of times in sort of that second step that we do where we want to convert things to moles, we'll use the volume and the molarity to do that. And also at the end of it, like on the very last step where we are in moles and we want to go some other unit, we also oftentimes will use the molarity equation. We may use the molarity equation to actually solve for the molarity. We may use the molarity if it's given to us in the moles to figure out the volume, like I think we did on a couple sort of titration problems last time. So again, really all stoichiometry problems are pretty much the same, except for really in most cases, how you get to the moles and at the end of the problem, what you kind of do with those moles. And in the case of solutions, usually, like I said, molarity gets kind of used there either at the second step and the last step, or at least the sort of second step there. Any questions on that? All right, so let's take a look at one more here, sort of titration problem. Let's say we had if we titrated, say, 25.5 milliliters of sulfuric acid with 42 milliliters of 0.225 molar potassium hydroxide. What is the molarity of the H2SO4? All right, so I want to take a moment there, see what you come up with. I'll do it as well because I just made up the numbers, so we'll hope for the best. Okay, so let's take a look, see how you're doing. So obviously here's some stoichiometry titration type problem. We do need an equation, so we're going to take our sulfuric acid here. Going to react it with some potassium hydroxide. That's an acid-base reaction, which you should know you get basically a salt and water. So the water, again, from the acid and the base is where we're going to get our H2O from. And again, our salt will be really the other guys, since this is really a double displacement reaction as they are switching partners here. Remember, we do want to make sure we get the right formulas first. So potassium is +1, sulfate is -2, so we will need a K2SO4. Secondly, once we have the actual right formulas down, remember that none of the stoichiometry works if it is not balanced. So in this case, it is not balanced, so we do need to put a 2 there. And I believe we will need a 2 there as well. Any questions on that? All right, taking a look at what we're looking for here. We are looking for the molarity of this acid. What we do know about the acid is we have 25.5 milliliters of it. For the potassium hydroxide, which is our base, we know the molarity is 0.225 molar. And we do know the volume of that we use, which was 42. So remember, ultimately here, we're looking for the molarity of our sulfuric acid. Out of that, we really do have the bottom part. We do have to do a conversion to liters, but we basically have the bottom part. So remember that really what we're kind of missing here for sulfuric acid is the moles, and that's really where kind of the stoichiometry part of it is going to come into play. And that's because we can definitely get moles of our KOH. And since we can get moles of our KOH, once again, we can use stoichiometry there to get to our moles of sulfuric acid. So the first thing we want to start with is to get the moles of the potassium hydroxide. Remember that we do need to convert our volumes into liters when we use it with molarity. So we got to do a little 1,000 milliliters is a liter, 0.042 liters. So taking 0.042 liters, we're going to multiply it by the molarity. Once again, I'm going to get rid of the big M here and use it more as a conversion factor where I could see both of the units. And in this case, I will want to keep the moles on top and the liters on the bottom here of HS2O4. The liters will cancel, and that's going to give me, wrong thing, that is KOH. Almost there, jumped the gun. But again, that's actually KOH. There we go. That will give me the moles of KOH in this case. So 0.042 times 0.225, going to give me 0.00945 moles of KOH. Once again, we ultimately need to get to moles of the sulfuric acid. So when we look at our balanced equation, we can see that for every 2 moles of the KOH, we basically have 1 mole of our sulfuric acid. So that would be our next step here in the calculation. We're going to go opposites to cancel. So the 2 moles of KOH will go on the bottom. The 1 mole of sulfuric acid will go on top. That's the stoichiometry part. And again, the part is going to get us to the right units that we need, which are moles here of sulfuric acid. And we will end up with 0.004725 moles of sulfuric acid. Again, basically our same sort of 4 steps. We want to balance the equation. We want to convert to moles. We want to do our mole-to-mole relationship. And now here's where, again, it kind of varies from a traditional stoichiometry problem. Instead of using molar mass or something like that, now that we have the moles here and we have the basically liters to begin with, we could actually go into the molarity equation. And that would give us 0.004725 moles, divided by my volume, which also needs to be converted into liters. So divided by 1,000, move that decimal place over 3 places. Going to give us here 0.0255 liters. And looks like we will end up with 0.185 molar sulfuric acid. And obviously, this would be our 4th step in this case. Any questions on any of those steps or solution stoichiometry? Now, obviously, you could also just start with molarity and volume, and at the end, use molar mass to figure out grams of something if you made a precipitate or something like that. Or you could start with grams and then also go into molarity at the end as well. Any questions on any of that stuff there? Yeah. Then the next thing we're going to talk about is some other sort of concentration units. And the next one we're going to talk about is percent by mass. It is sometimes referred to most of the time as mass percent, or percent m/m. And that is the, as it says there, the mass of the solute divided by the mass of the solution times 100%. And it is the bottom part that's really important. The mass of the solution. Remember that a solution is made up of two things, the solute and the solvent. So you want to make sure in these type of problems that you actually do get the total mass of the solution and not just the solvent. And that's because very commonly in these type of problems, they will give you that information separate from each other. So they'll give you how many grams of your solute, they'll give you how many grams of your solvent, and it's a very common mistake people make that they just kind of go with the solvent rather than adding it together. So you got to make sure that you really do add it together. There are a couple of other ones that are related to this, but basically, for example, if I had a 4.5% by mass sodium chloride solution, what that would mean if you wanted to turn that into sort of a usable sort of conversion factor, that would basically mean that I have 4.5 grams of sodium chloride in 100 grams of solution. So it's basically grams over grams here, mass over mass. You could also flip that around if you needed to and use it like a conversion factor, if you are given the sort of percent mass to mass. Sometimes, again, that's useful to do because you don't have to rearrange equations. You could just take it like a dimensional analysis, opposite units cancel, and it'll kind of do the math and rearranging the formula for you. As I mentioned before, in addition to percent mass to mass, there's a couple of other ones that are also similar. There's percent volume to volume, like in alcohol. That is the volume of solute divided by the volume of solution times 100%. Typically speaking, that's usually milliliters over milliliters. In terms of the volume is very commonly what you use. This one, you really don't have to be probably as careful with, because I will say usually in that case, they typically will just give you kind of the volume of the solution. They usually don't break it up. It really is that percent mass to mass. There's also a percent mass to volume, and that is the mass of the solute divided by the volume of the solution times 100%. That's basically grams to milliliters, kind of like density basically is a percent mass to volume. And they all work the same way. So if you had a 4.5% by volume sodium chloride solution, that would mean that you basically have 4.5 milliliters of sodium chloride in 100 milliliters of solution. Or again, you can flip it around, 100 milliliters of solution and use it as a conversion factor, you would have 4.5 milliliters of sodium chloride. Same thing with the mass to volume one. If you had 4.5% mass to volume sodium chloride, it would mean that you have 4.5 grams of sodium chloride in 100 grams, 100 milliliters of solution. Or in 100 milliliters of solution, there would be 4.5 grams of sodium chloride. So once again, they're all pretty similar in terms of how you calculate them, how you could convert them into a sort of conversion factor. Again, because these are percentages, we oftentimes assume 100, and what that does, again, is essentially keeps keeps obviously the numbers the same by assuming 100. Any questions on that there? All right, so let's just try one here, maybe. A solution is prepared by mixing 2.5 grams, kind of like 250, 2.5 grams of calcium chloride with 50 grams of water. What is the mass percent here? So what is the... Okay, so let's take a look. We're looking for the percent by mass there, basically mass percent. That again is our mass of our solute divided by the mass of the solution times 100%. Here it is the calcium chloride, which is our solute. That is the smaller part. And our water here is our solvent in this particular case. So we would put in there our 2.5 grams. Remember that the mass of the solution is both the solute plus the solvent. So here we do need to add. That would give us 50 grams plus 2.5 grams on the bottom, not just 50, because 50 would be just the solvent. So basically 52.5 we're dividing by. So 2.5 divided by 52.5 times 100% gives us 4.76% M/M, and you could put calcium chloride if you like in that particular case there. Any questions on that one there? So again, really important. A lot of times people will just go by actually the solvent there. All right. Want to try this one then? Concentrated hydrochloric acid contains 37.2% by mass HCl. How many grams of HCl are there in 35? Okay, so on this one here, obviously we're dealing with percent mass to mass. And again, that is our mass of our solute divided by the mass of the solution times 100%. So in this particular case, we are given the percent mass to mass, and that is 37.2%. We're looking for the mass of the solute. You may be wondering why. I know it's the mass of solute I'm looking for, and that's because remember that the name of the solution is the solute. So if you're looking for how much HCl you have in an HCl solution, you are looking for the solute in this case. That means the mass of my solution here was 35.5 grams. So you obviously could, if you like to, just plug and chug sort of into the equation there. You could also take a more dimensional analysis approach to the calculation, which is what I'm going to do. So basically that 37.2% means that I have 37.2 grams of HCl in 100 grams of solution. Or I could use it the opposite way as a conversion factor. 100 grams of solution would contain 37.2 grams of HCl. In this case, since I do have the mass of the solution, 35.5 grams mass of the solution, I could use a conversion factor here on the left, and it will basically cancel out. 37.2 grams of HCl, 100 grams of solution, 100 grams cancel. Going to leave you 13.2 grams of HCl, I believe, in this particular case there. Any questions on that? That, by the way, obviously is the exact same math you would do if you plugged it into the equation. You would take the 37.2, you would times it by 35.5 and divide it by 100%. Basically the exact same calculation, obviously. Here, you don't have to worry about rearranging. You just got to think about opposites in dimensional analysis. It rearranges it basically for you correctly. Any questions on that there? So another unit of concentration that we come across sometimes is our friend here, molality. And molality should not be confused with our other friend, which is capital M, molarity, moles per liter. This is molality, which actually is lowercase m, and it is moles of solute divided by kilograms of solvent. So that's the kilograms of solvent. By the way, Jeopardy question here. If you want to go from molality to molarity, you need density to do that. Yeah, so density is typically the thing that will allow you to kind of go back and forth between those two things most of the time. So again, we do abbreviate it with the little m, and kind of just like the molarity, if you do have like 4.5 little m there, or molal. You probably also want to kind of just turn it into both units so you can see them. And once again, that'll help you maybe not miss a unit or something like that when you are doing the calculation. Molality is a common concentration unit that is frankly used for what we'll talk about in chapter, I want to say 10-ish maybe, which is colligative properties. There are in a lot of those sort of formulas, molality and stuff like that. So why don't you try one here? Calculate the molality of a solution that's prepared by dissolving 61.7 grams of C3H7OH in 175 milliliters of water. The density there of water is 1 gram per mil. Okay, so if we look at this here, the C3H7OH, that's going to be our solute. Water here will be our solvent. And again, we're looking for the molality, which is our moles of solute, kilograms of solvent. So in this case, we do need to convert our grams into moles. So we do need to go to the periodic table to do that. So our carbon would be 12.01, our hydrogen right at 1.008, and our oxygen there at 16. So if we add up everything there for our molar mass, that's going to be 3 times 12.01 plus 8 times 1.008 and a 16. We got a 6009, it looks like. 6009. So 6009 grams per mole is our molar mass of our C3H7OH from the periodic table. Using that to get our grams into moles, which is what we need here up on top. Again, using the molar mass here as a conversion factor, 6009 grams on the bottom, moles up on top. And that will get us here 61 points divided by 6009. It looks like 1.037 moles. So that's going to be up on top. We now need kilograms of our solvent. Once again, here, water is our solvent. And we do not have the mass of the water, but we do have the milliliters, and we do have the density of water, which is 1 gram per milliliter for water. That would give us that we basically have 175 grams of water. Remember, though, that we actually need it in kilograms, so we got to do that conversion there. That's 1,000 grams is a kilogram, and that will get us 0.175 kilograms in this case. And that obviously is the bottom of what we need. So lastly here, to get to our molality, we'll take our moles. We'll take our kilograms of solvent, 0.175 kilograms. And we will end up with here, looks like maybe like a 5.87. Now, in terms of the units, it is very much like molarity. You could really leave it one of two ways. You could leave it with the 2 units, moles per kilograms. Or just like molarity, you can just put a little m next to it, and that would be molality. So you could do it either way in this case. Any questions on that one there? So we definitely will see molality pop up in a number of places a little later on in the semester. Questions on that there? Lastly, as well, another sort of calculation that will actually pop up in the next chapter and also later on as well. This is what is referred to as the mole fraction. Now, the mole fraction is basically a percentage without making it a percentage. So you basically calculate like you would calculate a percentage, just don't multiply it by 100, and you get basically point something rather than, up to 100. So when you add up all the mole fractions, they should equal 1, which is basically equivalent to 100% of what you got going on. How do you calculate the mole fraction? Mole fraction is abbreviated usually with an X, and on the bottom is whatever you're trying to calculate the mole fraction for. You basically take, much like the name implies, you take the moles of what you're looking for, and then you divide it by the total moles. Once again, here we do not multiply it by 100 to make it a percentage, so you'll get like a point something type number for everybody, but which again, they all should add up basically to 1. We see mole fraction in the gas chapter. We also again see it in the colligative properties, along with molality will be there as well. So let's take a look at one here. What is the mole fraction of methyl alcohol in a solution that's made up of 0.328 moles of methyl alcohol and 0.929 moles of ethyl alcohol? So take a moment there and calculate it up. Okay, so we're looking for the mole fraction here of methanol, basically. So basically, that's going to be our moles of our methanol divided by the total moles. Obviously, in this particular case, they gave us everything in moles, but if you had things in grams, you would use the molar mass to convert to moles if we need to. So pop it in our numbers here. We'll go with a 0.328 moles up on top. We're going to add both of those guys together to get our total moles, which I think, by the way, will get you 1.257 moles if you do that. 0.328 divided by 1.257 will get us 0.261 is the mole fraction. Basically, what that means is like 26% made up of that is pretty much what that means. If we wanted to do the other one, we could do the same calculation. X for our ethanol. Our ethyl alcohol would be 0.292 divided by 1.257 moles, which is our total moles. And that would get us basically the mole fraction of this guy, and about 0.739 in this case. By the way, I didn't even need to do that calculation because it all should add up to 1. So I could actually just did 1 minus this guy, and it would give me this number here. So you could have done that as well, since that was the only other thing that was left there. So basically, I take it 100% minus the other percentages is essentially what you're doing there. Any question on mole fraction here? All right, that should wrap up this one. We are off then to chapter 8, which is gases. So we're going to talk about some gas laws, some of which maybe you've remember seen before. We'll probably talk about maybe a few that you haven't seen before. But funness with gas, right? All right, so gases obviously is a state of matter where everybody has broken apart from one another. They're flying around. And one of the main properties of gases that we associate with it is pressure. So that's one of the main sort of properties that we associate with it. The pressure of a gas is really based on how many collisions there are. So as they are flying around, right, they're colliding with the walls of the container and such. And the more collisions that you have, that usually obviously results in a higher pressure, and vice versa. Less collisions, a little bit lower of a pressure. Now, when we talk about gases, let's first talk about really substances that sort of exist as gases under normal conditions. And when we talk about sort of normal conditions, we are talking about sort of everyday conditions, and that usually refers to a pressure of 1 atm, which is an atmosphere. So that is a unit of pressure. And usually the temperature that we sort of think about as like normal everyday sort of temperature is 25 degrees Celsius. And under these normal sort of conditions, if we had an ionic compound, they essentially will not go into the gas phase or be found in the gas phase under these conditions. And that is because ionic compounds are held together by probably one of the strongest sort of intramolecular forces, which is the force within a molecule. That's that electrostatic attraction. Opposites attract to each other, positive, negative attraction of the ions. You essentially could heat the heck out of an ionic compound, and it probably will just start to melt before it'll actually go into the gas phase. Because again, it's held together by really, really strong forces. Now, that's different than when we deal with molecular compounds. Molecular compounds, basically like carbon monoxide, carbon dioxide, hydrogen gas, ammonia, and CH4, which is methane, like what comes out when you light a Bunsen burner. These guys are gases under normal conditions, but different than an ionic compound in a sense is molecular compounds oftentimes at normal temperatures are found either as a solid or a liquid. But the major difference between that and an ionic compound is it is usually much easier to convert a molecular compound, which is basically guys that are sharing electrons that hold themselves together, um, into a gas than it is, say, an ionic compound. And that really has to do with something that's known as intermolecular forces. And intermolecular forces essentially are, as we'll talk about in perhaps the next chapter, I think, but essentially they are the forces that hold one molecule together with another. And how they all work pretty much is a really simple arrangement. Pretty much the positive side of one molecule is attracted to the negative side of another. And that force is what's known as an intermolecular force. For example, the most common example of this that we're all familiar with is our friend water. Water is a polar molecule, like we talked about with bonding, where oxygen is more negative, the hydrogens are more positive. So when two waters come together, they're actually attracted to each other by the negative side of one to the positive side of another. And this is what is known in the case of water as hydrogen bonding. Hydrogen bonding is a pretty strong intermolecular force. It holds together basically, for example, these water molecules. And that's different, for example, if you just took one water molecule by itself, the covalent bonding between the oxygen and the hydrogen where they're sharing electrons, that's actually the intramolecular force. For one water molecule is basically the covalent bonding. Now, when we deal with intermolecular forces versus intramolecular forces, the intermolecular forces are always weaker. And we know that because when we go and take something like water and we heat it, the first bond that breaks is this bond, the bond between two water molecules. And that bond breaks first. It allows this water molecule and this water molecule basically to go off and fly off and become into the gas phase. If it was opposite and these individual bonds were weaker, which is the intramolecular force, when you would boil water, you would make hydrogen gas and oxygen gas, and that would not probably be good if you're boiling water and you start making hydrogen gas and oxygen gas. So we know that doesn't happen. So again, this kind of weaker intermolecular force, the hydrogen bonding in this case, is actually the first force that gets broken, and that's what allows those guys to go into the gas phase. That's also why something like methane here is a gas, and why a lot of organic compounds are gases, especially those first few, like methane, propane, butane, they're all gases. And that's because these guys are pretty much nonpolar molecules. And these nonpolar molecules, as we will talk about, use an intermolecular force, which is known as dispersion forces. And in the realm of intermolecular forces, that's pretty much as weak as you could get it, is that type of force. And as we'll talk about in the next chapter, essentially it is a temporary sort of attractive force. And that's because they're nonpolar, they don't have a positive side or a negative side like a polar molecule. So they have to rely upon something happening to temporarily give them this sort of charge that allows them to interact with stuff. So because of that, even when a couple of methanes get together, you could just look at them wrong, and that's enough for them basically just to want to go apart. That's also why a lot of organic molecules are what are referred to as being volatile, which means they could go into the gas phase really easily because they're not held together very tightly, which means even though they started in liquid phase, you just leave them long enough and they're going to find their way away from each other, which is why when you take organic chemistry, they throw you in a fume hood So you hopefully don't have that happen. You don't have to smell it. Or more importantly, a lot of them are flammable, and that's not a great thing when it just goes in the gas phase really easily and they're flammable. You hopefully won't set the place on fire. So when we have a molecular compound, you can much easier convert it into a gas than say an ionic compound. And typically speaking, the stronger the attractive forces between a molecule and itself, the less likely you would find it in the gas phase under normal conditions. And as we'll talk about when we get to that chapter, intermolecular forces affect things like solubility, boiling points, melting points, and how things basically interact with each other. So what substances are gases under normal conditions? Well, they are our normal sort of ones here. There are a lot of those diatomic molecules that are elements. So hydrogen gas, nitrogen, oxygen, fluorine, and chlorine. Ozone is also a gas, which is O3. And then, of course, we can't forget our group 8, which are the noble gases. They are what are referred to as being monoatomic, which means they come as ones, basically, all those guys, as opposed to, say, hydrogen, nitrogen, oxygen, which comes as twos, which is why they are diatomic. So if you look at the periodic table there, pretty much that's your run there in blue is all of our sort of under normal conditions, we would expect to find these guys as gases. So let's talk about some physical characteristics of gases. Gases assume basically the volume and shape of their container. So as they are flying around, they're filling the container they're in sort of uniformly as they're flying around, obviously colliding and stuff like that. Gases are the most compressible state of matter. You can't really compress a liquid too much without making a mess in a lot of cases. And gases will mix evenly and completely when they're in the same container. So just by the process of a gas in the same container, they're flying around. So they're just constantly mixing with each other right as they're flying around. And gases have a much lower density than liquids or solids. And we're going to talk about in this chapter how to calculate the density of a gas. So normally when we think about density of, say, liquids or solids, usually the units are grams per milliliter or grams per cubic centimeter. But when we deal with gases, usually the units are actually grams per liter is the typical unit that we use for the density of a gas. Now, we do measure pressure, which again, as I mentioned, is a common unit of gases and pressure. And there are a few different sort of units that we use. This right here is a barometer, classic barometer. A classic barometer usually would have mercury in it and a glass tube. And as the atmospheric pressure would push down on the pool of mercury, the mercury in the tube would rise. And as we might have talked about along the way, mercury is one of those weird sort of elements that actually will have a upside down meniscus. So mercury's meniscus will actually go upside down rather than the typical U-shaped meniscus. And if you were going to take a reading in mercury, you would actually read from the top of the meniscus there because, again, it kind of goes this way. Now, when we talk about pressure units, there's a few different types of pressure units. There are pascals and kilopascals, which are very common. Pascal is also 1 Newton meter squared. I would say for chemistry, this is probably our big three. That is the units of atmospheres, millimeters of mercury. It is called millimeters of mercury because, frankly, a barometer used to have a ruler on the side of it. And you basically would take a reading on the ruler. A lot of times it's in inches or centimeters of mercury, or sometimes millimeters of mercury. So that's what basically that stands for. It also equals 760 torr, named after Torricelli, which is the guy who invented the barometer, is why that is named as well. 1 millimeter of mercury is equal to 1 torr. It's a 1-to-1 relationship between those. And 760 is an important number because that is the conversion factor to go from atmospheres to millimeters of mercury or torr. You need to basically multiply by 760. And if you have millimeters of mercury or torr, and you want to go to atmospheres, you need to divide by 760. So that 760 is a really sort of good conversion factor. 1 atmosphere is equal to 101,000 pascals, or about 101.3 kilopascals, if you want to do that. There's other units of pressure as well, PSI, right? Pounds per square inch. And also there's bar, for example. A bar is like 1.01 atmospheres. Basically, they're almost equal to each other. There's other sort of units that we see. Now, as we obviously go above sea level and get further away, you can see that the pressure decreases, right, as we go up there. Hence why when you fly in a plane, they pressurize the cabin and all that good stuff, right? It's because you're very high up, right, above sea level as you're flying around. So one way that we can measure pressure of gases is to use a manometer. And there's two types. One that's kind of closed up on top. So there is no sort of atmospheric interference of pressure. It's in a vacuum. So basically the idea here is you have a gas, and basically the gas pushes the mercury. And you can actually measure the height of the mercury column. And from that, you could basically calculate the pressure associated with it based on the height there. In this case, it's a open situation, which means you do have actually atmospheric pressure pushing back down on it. So you do have to take that into account here. Same idea. You would measure the height of the mercury in the column, and you would also have to take an adjustment there for basically the atmospheric pressure as well, kind of pushing back down on it. And that would get you your pressure of your gas. So those are two common sort of units that are used. So we're going to talk now about some gas laws. And really, when we talk about gas laws, there's three variables that we oftentimes deal with: pressure, volume, and temperature. And in certain cases, we keep maybe one thing constant and vary a couple of the others, or sometimes we just vary everything along the way. So the first sort of relationship we're going to look at here is basically the relationship between pressure and volume. And in this situation, this is going to be at constant temperature. And what we see here, if we look at basically each of these sort of manometers here, we have 100 in terms of our volume. Then it comes to 50 in terms of our volume, and then it comes to 33 in terms of our volume. And what we see in terms of the pressure here, that is the pressure when we have 100, we cut the volume in half. Now we have this much pressure sort of happening, and much more pressure. And we cut it even smaller. Now we got, this much more pressure basically happening. So the relationship that we see when we look at pressure and volume is as the volume gets smaller. Basically, if you just think about it logically, you have a very small volume, you have gas molecules flying around. That is definitely going to increase the number of collisions because they don't have very far to go to hit a wall, basically, right? So because the volume is really small, collisions will go up. The result of that is we will see the pressure increase. Opposite is true if you give everybody a little bit more room to fly around in. They have a much larger volume, which means it's going to take a little longer for collisions to occur. The number of collisions will come down, and so will the pressure. So as the volume goes up, the pressure will go down. And that's essentially what we see here. This is also the relationship known as Boyles Law. Boyle studied this relationship of pressure and volume, and that is what happens with Boyle's Law. Pressure goes up, volume goes down. Volume goes up, pressure will go down. So when we look at Boyle's Law, we see this sort of inverse relationship here. And there's an interesting thing that we do see, which is, again, as we just talked about, at a much lower volume, we have a much higher pressure. When we open up that volume much larger, we end up with a much smaller volume. Now, one interesting relationship is if you take a gas and you take a bunch of pressure and associated volume relationships with it, no matter what pressure or volume you take for that particular gas, if you multiply them together, you get a constant number, sometimes referred to as a proportionality constant, little k. And you could take for that gas a bunch of measurements and always take the pressure times the volume. You'll get the same relationship. Because you get the same number when you do that, you could actually set it equal to each other. And that gives us the form of Boyles Law that you might be familiar with, which is P1V1 equals P2V2. This again is at constant temperature. And this is what we saw here, increase in volume, decrease in pressure, decrease in volume, increase in pressure. If you take the pressure over 1 over the volume, you get a nice perfect linear relationship that occurs. In this particular case, the pressure units does not matter as long as they are the same on both sides, so everything cancels out correctly. And same thing with the volume. The volume units don't matter either, again, as long as they are the same units on both sides. Any questions on that there? All right, so let's try one there. Sample chlorine gas occupies 946 at a pressure of 726 millimeters of mercury. What is the pressure in millimeters of mercury if the volume goes to 1? At this, obviously, at this point, we only have one equation to choose from, but that will shortly change. We'll have a number to choose from. Really good way to sort of work gas law problems is really just to pull out the information and label what they are. So clearly here I have a volume that's 946 milliliters. It goes with a pressure to 726 millimeters of mercury. We are looking for a pressure, and we have another volume that's 154 milliliters. So again, just kind of labeling it, you could kind of see Boyle's Law sort of appearing. Doesn't matter which ones you call ones and twos. The answer really is no, as long as you keep the numbers that go together. So as long as you keep them together, it doesn't really matter. Traditionally, people just roll with whatever comes first in the problem is the ones, and the next ones are the twos. In terms of units, my volume are both the same, so that's good. My unit of pressure is millimeters of mercury, which just means when I solve for it, it'll be millimeters of mercury. Other thing about gas laws is pretty much the easy way to rearrange things is if you move it something to the other side of the equal sign, it ends up in the opposite location. So in this case, we are looking for P2. This guy, they are both up on top on the right, which means when I move it across the equal sign, they end up on the bottom, basically dividing. And that would give us P1, V1, V2 is equal to P2. And popping in our numbers correctly here, hopefully 726 millimeters of mercury, 946 milliliters, all divided by 154 milliliters. Milliliters is going to cancel. That once again will leave us millimeters of mercury as our unit of pressure here. So 726 times 946 divided by 154. Going to get us about a 4460, we'll call it. And that is millimeters of mercury in this particular case, right? First off, any questions on that? By the way, this is again Boyle's Law relationship, and we can see if it makes sense. Here, our volume went from 946 to 154. That means our volume went down. That means our pressure should go up. And it started at 726 and ended at 4,400. So it did go up. It went in the right direction. So understanding the relationships of what happens to one versus the other sometimes can help you in case you inverse a number or something like that, and make sure that at least hopefully your numbers sort of make sense. Any questions on that there? All right, let's try another one here, perhaps. Yep. Inflated balloon has a volume 0.55 liters at sea level, which is 1 atmosphere. It rises to 6.5 kilometers, where the pressure is 0.4. Assuming the temperature remains constant, what is the final volume of the... All right, so once again here, I'm going to pull out the information. I got a volume 0.55 liters. 1 atmosphere is a pressure. 6.5 kilometers is useless information in this problem. Pressure 0.4 atmospheres. And I am looking for a volume. So once again, you should hopefully be able to recognize our Boyle's Law happening here. I'll call these guys ones, these guys two. My pressures are both in atmospheres, so I'm good to go on that. Again, here we're going to divide this to the other side, which means it will end up on the bottom. And that will give me P1, V1, P2 is equal to V2. And putting in our numbers there, 1 atmosphere, 0.55 liters divided by 0.40 atmospheres. Atmospheres cancel. In this case, my units are going to be liters in this case. So that's going to be a 0.55 divided by a 0.4. That's going to be a 1.4 liters in this particular case. Once again, if we want to kind of make sure, hopefully we're on the right track, our pressure was at 1, it ended at 0.4. In this case, our pressure went down, which means our volume should go up. Started at 0.55 and went up to 1.4. So again, that makes sense based on what should happen in Boyles Law relationship. Question on Boyles Law there. All right, the next sort of relationship we're going to talk about will actually deal with volume and temperature and also pressure and temperature and sort of see those effects. So the next two sort of relationships is basically our friends here, Charles' law, which is basically V1 over T1 is equal to V2 over T2. And this is actually at constant pressure. There's also Gay-Lussac's law. And that is P1 T1 is equal to P2 T2. And this is actually at constant volume. Now, when we think about what happens in this particular situation for each of these cases, we'll start with Gay-Lussac's law over here. If I have gas molecules in this container and I increase the temperature, I would expect my gas molecules to start to fly around a lot faster. And because they're going to start flying around a lot faster because you increase the temperature, have more energy, that is definitely going to lead to a bunch of collisions occurring. And it can lead to more collisions occurring. And what that's going to do to the pressure is it's going to basically increase the pressure because we're going to have a lot more collisions basically happening, and that will result in more pressure. Now, if I have the same gas molecules here in the same container, but I lower the temperature, what's going to happen is those gas molecules are now going to lose some energy, and dramatic drawing here, they're going to move around a lot slower, right? So they're going to fly around a lot slower. And because they're flying around a lot slower because of the lower temperature, the result of that is we will have less collisions actually happening, and we will actually see the pressure start to decrease. So in the Gay-Lussac sort of relationship, because we have this constant volume, the volume is basically fixed. It's a rigid container, nothing's going to move. As you increase the temperature, because everybody's flying around faster, we'll have more collisions, and that will result in more pressure. And as you lower the temperature, everybody will fly around slower, less collisions and less pressure. Now, that is different than what we see with sort of Charles' law relationship. And that is basically the idea here is we want to keep the pressure constant. So when we have a gas molecules in a container and we go to increase the temperature, if the volume is fixed like it was over here on the right-hand side, what we know is going to happen is we're going to see that big increase in pressure. And we kind of want to avoid the big increase in pressure. So what ends up happening is, all right, our gas molecules are now moving around a lot faster. What needs to happen is actually the volume will adjust, and the volume will adjust bigger and become larger. So even though those gas molecules are now flying around faster, they have a much longer way to go to hit the wall. And that will result in basically the number of collisions staying constant. And that's how basically it's able to keep the pressure constant. So as the temperature increases, we actually see an adjustment in the volume in this case of Charles' law. And that adjustment in the volume is what allows the collisions to stay the same. And again, keep that pressure from going crazily up like it would over there in Gay-Lussac's law if the volume didn't move. Opposite is true as well if we kind of lower the temperature here of this guy. we're going to have our gas molecules again moving much slower. And if the volume stays the same, we will end up just like we were over here. We will start to see the pressure start to drop because they're moving slower, slower moving, less collisions. So what happens in that situation is the volume actually gets smaller. So the volume actually comes down. And what that does is, because it squishes the volume together, now those gas molecules that are not flying around as fast don't have as far to go, and they can hit collisions and keep the number of collisions, again, relatively constant. So in Charles' law situation, the way it's able to maintain constant pressure is actually the volume that adjusts with the temperature. And if things are moving faster, volume gets larger, gives everybody a little bit more room to fly around in. And if the temperature goes down, they squish everybody together. So since they're not moving as fast, they will have the number of collisions remain basically the same. We don't get that volume adjustment in Gay-Lussac's law because, frankly, the volume is fixed, so you don't have that adjustment. So we definitely see the pressure start to change as the temperature changes. Any questions on that? Now, a really important one for this gas law and other gas laws is this graph right here. And this graph right here is a graph of volume versus temperature. And you can make this graph here of volume versus temperature for any gas you like. And if you take all those lines back to the temperature, you will always hit this number, minus 273.15 degrees Celsius. That number should look familiar to you because that is the number we use to convert to Kelvin. Yeah, if you add 273.15 to it, that is what we call absolute zero, or 0 Kelvin, right? Kelvin recognized the nature of this, and because he recognized the nature of this, you pretty much can thank him for every time you use a gas law, temperature needs to be in Kelvin no matter what the situation is. It should be a no-brainer for you. It should be the very first thing you do when you're doing gas laws is, I'm just going to convert these guys to Kelvin. Yeah. Now, the volume doesn't matter. It could be whatever unit you want as long as they're the same, but the temperature needs to be Kelvin. Same thing for our Gay-Lussac's law. Our temperature here does need to be Kelvin as well. And the pressure in this case can also be any unit you want as long as they're the same on both sides. Pretty much any gas law that you're dealing with and you have temperature, it needs to be in Kelvin. And like I said, that should be really the first thing that you do. Even in a problem which sometimes confuses people, where they give you the temperature in Celsius, they want you to give the answer in Celsius. So people think in that situation, I'm safe just to leave it in Celsius and put it into the gas law. You're not safe. You will get it wrong and you will get an X on it. So don't do it. So you do need to take it from Celsius to Kelvin. You got to pop it into the gas law in Kelvin and then take it from Kelvin back to Celsius and that type of problem. So it's a very common mistake people make when they see a problem like that. They're like, they gave it to me in Celsius. They want it in Celsius. Why do I need to do the conversion? So in order to get the right answer, you do need to always do the conversion when you go into a gas law. Pretty much any gas law with temperature, Kelvin needs to be done. So that's usually one of the first things that you want to do when you're doing one of these type of problems. Any questions on that there? All right, I think we will